We introduced previously the ideas of feedback control, feedback in amplifiers, and we saw the general structure of a feedback system and the four basic feedback topologies that depend on whether the input quantity is a voltage or a current, and the output quantity is a voltage or a current. So these are the four topologies that we introduced. And now we will consider the voltage amplifier. So this is when the input is a voltage and the output is a voltage. I want to consider the case where I have the amplifier without feedback. This is my original amplifier. Inside the gray block, it has an input resistance Ri, an output resistance Ro, and an open circuit voltage gain A. This amplifier is now used in a feedback loop with this beta block. This is the beta block. And you see here that we are sensing the output. And producing a feedback quantity, which is also a voltage from the output voltage, Vf equals beta Vo. That is subtracted here from the source by connecting it in series with it. We call this case the ideal situation because I assume that this beta block, the block inside the blue block, the blue square, does not affect the output. So you see here an open circuit, which means that I am measuring the output without affecting it. This is an ideal situation because usually when you do that, you may affect the output. The other ideal situation is that the source is an ideal voltage source without a source resistance, which means that whatever I connect to it, the voltage across its terminals will be the same. There's no R sig or RS. Still, this exercise is useful in verifying the feedback, the gain of the amplifier with feedback, and the effect on input resistance and output resistance. So now I want to consider the amplifier with feedback as if it's a new amplifier. So now what's inside the red block, the red square, I want to consider it as a new amplifier. So this is the new amplifier with feedback. And I want to find the gain VO over VS for the whole thing. I also want to find the input resistance of the red new amplifier and the output resistance of the red new amplifier. So this is my feedback system with the original A inside the gray block. And this is my new amplifier with feedback. I want to find its voltage gain now, which is VO over VS. VO over VS, we can easily show that it's A over 1 plus beta A. And that's not a surprising result. We can show from the circuit that VO over VS is this formula given by general feedback, general negative feedback expression. A over 1 plus beta A. And you can see it from the circuit. You can easily show that because there's no load here on VO. So VO is A times VI. And VI is the voltage here. And by KVL, You can do a KVL here. So VI plus VF equals VF. And of course, VF is the voltage here, which is equal to beta VO. These are the same equation we wrote previously, but it was XO and XI and XS and XF. So same equations would produce the same equation. The gain with feedback is the original gain, A, of the amplifier without feedback, divided by 1 plus beta times A. I would like to know what is the input resistance of this amplifier with feedback. So this is the input current here. This is the input of the amplifier with feedback. And this is the input voltage. So Ri with feedback would be Vs over II. But II is the same current flowing here. So it's also Vi over Ri. Ri is the input resistance of the amplifier without feedback. And we can write this as Ri times Vs over Vi, which can be written as Vs over Vo times Vo over Vi. Vs over Vo is 1 over AF, and Vo over Vi is A. And this gives us that the input resistance with feedback, RIF, is Ri times 1 plus beta A. So the input resistance of the amplifier, of the feedback amplifier, the red amplifier, is equal to the input resistance of the original amplifier without feedback times 1 plus beta A. And we know that for negative feedback, beta A is positive and 1 plus beta A is larger than 1 and maybe much larger than 1. And this means that the input resistance of the feedback amplifier is larger and possibly much larger than the input resistance of the original amplifier. For output resistance, we can also do the output resistance calculation from the definition. So we set the input to 0, and we connect a test source at the output. So Vx is the test source across the output, and we want to find Vx over Ix. When I set the input to 0 for the amplifier with feedback, this means that Vs is 0. And if I set Vs to 0, then Vi would be minus beta times Vx. And then I can find Ix, and I get Ix is Vx plus beta A Vx over Ro, and this will give me Vx over Ix, which is the output resistance of the feedback amplifier. Rof is the original output resistance of the amplifier without feedback, Ro, divided by 1 plus beta A. So this is the Ro of the amplifier without feedback. And for the amplifier with feedback, inside the red box, the output resistance would be that, the original, divided by 1 plus beta A, and therefore it's smaller and possibly much smaller than the original output resistance. So now, is this an improvement or not an improvement? For a voltage amplifier, the ideal input resistance, if I want the best input resistance I can hope for a voltage amplifier, that it would be infinity. Ri ideal for a voltage amplifier is infinite. RIF is Ri times 1 plus beta A. So RIF is greater or possibly much greater than Ri. So the effect of feedback is to take this Ri and make it bigger. So it's moving it towards ideal. And therefore, that's an improvement. If you take the input resistance, apply feedback, and it increases in a voltage amplifier, then it's going in the direction of becoming closer to ideal, and therefore, it's an improvement. So feedback is helping us in this case by increasing the input resistance of the voltage amplifier. For the output resistance, we said that it's less than RO and possibly much less than RO. The ideal output resistance of a voltage amplifier is 0, as a short circuit. So the smaller, the better for a voltage amplifier. For output resistance, the smaller, the better. And feedback is therefore taking us in the direction of ideal, because it's reducing the output resistance. Because it's reducing the output resistance, it's making it closer to being ideal. So that's also an improvement. This means that feedback improves input resistance and improves the output resistance. In the case of voltage amplifier, by increasing the input resistance and reducing the output resistance. So again, that's another advantage of using feedback in terms of input and output resistances. We can do a similar analysis for the 4 cases of amplifiers that we talked about. So for the transconductance amplifier, this is the ideal situation. It's very important to note that for the transconductance amplifier, the output is a current. The output quantity is a current. Transconductance amplifier is a voltage controlled current source. So it's controlled by an input, which is a voltage, to produce an output, which is a current. So in this case, the ideal situation would be a short circuit at the output. And the ideal beta would have a short circuit here, because the output quantity is a current. A of the original amplifier, because this is a transconductance amplifier, produces a current from a voltage. A has units of amp per volt. A is a transconductance. So A has units of amp per volt. Beta always has units that are opposite to the units of A. So beta takes the output current here, current, to produce a voltage. And therefore it has units of volt per amp. So the units of A in a transconductance amplifier are amp per volt, and beta is volt per amp. And A times beta should have no units. So for this transconductance amplifier, where the input is a voltage and the output is a current, the gain formula is the same as what we saw previously. And remember that the gain is output current divided by input voltage. The input resistance, we can show from this circuit that it increases. And also, we will find that the output resistance also increases. So like the voltage amplifier, the input resistance increases. But unlike the voltage amplifier, the output resistance decreases and increases in this case, while it decreases in the voltage amplifier. So is this going in the wrong direction? Actually, no, because the input is a voltage. And if the input is a voltage in the transconductance amplifier, I would like the input resistance to be as large as possible. So feedback is taking us in the right direction towards larger and larger input resistances in this case, and therefore it's helping. It's improving the input resistance. For output resistance, since output is a current, because the output is a current, and remember when we talked about the current mirror and current source, we said that we would like the output resistance of those sources to be infinite, to be as large as possible, so that the current is constant. In this case, we can use the same argument. Because the output is a current, I would like the output resistance to be as large as possible. ideally infinite. And again, feedback, because it's increasing the output resistance here in this amplifier where the output quantity is a current, is helping us, is helping in making the output resistance closer to being ideal. So again, feedback is improving both the input resistance and the output resistance. For this particular case of transconductance amplifier, the improvement is by making them larger. So that's the situation with the transconductance amplifier, where the input is a voltage and output is a current. The third type is the transresistance amplifier, where the input is a current and the output is a voltage. And here, A is the gain, and it takes a current to produce a voltage. So it has units of volt per amp. Beta measures the output voltage, senses a voltage to produce a current. So beta has units of amp per volt, again, opposite units. We can show from this circuit that with the input being a current, output being a voltage, with current mixing, voltage sensing, we can reach the same equation. So this gain equation is always consistent. Gain with feedback is the gain without feedback divided by 1 plus beta A. We can also analyze the circuit C to find its input resistance, and we will get this result, that the input resistance is the original one of the amplifier without feedback over 1 plus beta A, which means that the input resistance is decreasing. Output resistance also, we can show it's RO over 1 plus beta A. So the input resistance becomes smaller because of feedback, and the output resistance also becomes smaller. And these are the right directions for this kind of amplifier. Because the output quantity is a voltage, I would like the output resistance to be as small as possible. So that's good, because the output quantity is a voltage. Because the input quantity is a current, I would like the input resistance to be as small as possible also. And this is going in the right direction also. So again, for this type of amplifier, where the input is a current and the output is a voltage, feedback reduces the input resistance and the output resistance, and therefore improves them by taking them in the right direction towards the ideal value. The fourth type is the current amplifier, where the input is a current and the output is a current. So A and beta in this case have units of amp per amp. And again, we can show that the gain is reduced. It becomes the original over 1 plus beta A. And this 1 plus beta A divides the input resistance, but multiplies the output resistance. And again here, because the input quantity is a current, the ideal input resistance for an input current is 0. And therefore, feedback is taking the input resistance in the right direction towards ideal by making it smaller. Output resistance, because the output quantity is a current, output resistance is also increasing in the right direction, because the ideal output resistance when the output quantity is a current is infinite. So again, feedback is improving input resistance and output resistance in the right direction in this case also. So in all cases, the input resistance is improving and the output resistance is improving, depending on whether the input quantity is a current or voltage and the output quantity is a current or voltage. We get either a multiplication by 1 plus beta A or a division by 1 plus beta A, so that the quantity RIF, input resistance with feedback, or ROF, output resistance with feedback, moves in the right direction. Okay, so this was an overview of the effect of feedback on all these types of amplifiers. Let's show a feedback amplifier, starting with the system flow diagram. So this is what we had, the sigma and the A, and the output and the flow direction here. We call this quantity xi, this quantity xs here coming to the sigma, and this is the beta block here that takes the output xo and produces a feedback quantity xf that is subtracted from xs to produce xi. This is a general block diagram for feedback systems, not necessarily just amplifiers or circuits. Let's try to implement a feedback amplifier using components that we're familiar with. Because I need a plus and a minus, I need here to subtract two signals and produce something, an xi as a result. Maybe I can use an op-amp. An op-amp can do this. It can take two inputs and produce an output which is proportional to the difference, and therefore it's kind of calculating the difference between them, it's subtracting them. All right, so this is my XS or VS, voltage in this case. All right, so I'm implementing this part here, XS going to the sigma, is VS going to the plus input of the op-amp. Now I want to subtract from XS, XF. So XF should come here to the minus input from the beta block. So I don't need really to worry about building a circuit for sigma because I have the op-amp, and the op-amp internally will take the difference between the two inputs. So the op-amp will take care of that, will implement sigma for me here internally. And we know that the op-amp has large gain, large A, and will produce an output. So also the op-amp internally is implementing the A block. So I don't need to have another component to implement A. The op-amp does that for me. So actually the op-amp is sigma and A together and produces an output. So that's the XO or VO in this case. Now I still need to implement the beta block. So I want to take this VO output and produce beta times VO. I want to take a voltage and produce like a fraction of this voltage to have VF here. So one way to do that is to use a voltage divider. Usually the VF is less than VO. And if I want to like divide VO to get VF, like multiply VO by 0.2 or 0.25 or whatever, I can do a voltage divider. So here's a voltage divider. And this voltage divider, let's call this R1 and this R2. This voltage divider, because there's no input current into the op-amp, This voltage divider actually will give me VF is the voltage divider formula R1 over R1 plus R2 times VO. So that's my beta, R1 over R1 plus R2. So this is an example of a feedback amplifier where we implement the beta block using a voltage divider with 2 resistors. And we implement the sigma and A blocks with an op amp. Now let's see. This actually looks familiar. If you look carefully at this and redraw it, flip the op amp, let the minus be above. Let this be minus here and plus here. So VS is here. I'm just redrawing the circuit. It's the exact same thing. And this is VF. And there is R1 to ground. So that's R1 to ground. And there is R2 between VF and VO. And that's VO. This becomes exactly this by just redrawing the circuit. We're making the minus here and the plus here. And if I do that, you will notice that this is the non-inverting op amp amplifier configuration. So what we're familiar with, this non-inverting op amp amplifier configuration, is a very nice illustration of a feedback system. We did not analyze it as a feedback system, but now we can. Now we know how to do that. In fact, let's do that. And this is beta, right? This is beta, R1 over R1 plus R2. The amplifier open loop gain is A. So would the feedback equation give me the correct answer? I know what is the gain of this. It's 1 plus R2 over R1. This is a well-known result. So feedback will tell me that AF in this case is A over 1 plus beta A. Okay, so A over 1 plus beta R1 over R1 plus R2 times A. So this is AF. But this is not the same as this. This is not the same as 1 plus R2 over R1. So why? Well, there is a very simple reason. Here, when we derive this equation, we assume that A is infinite. And if I take the limit of AF as A goes to infinity, what do I get? I get A over R1 divided by R1 plus R2 times A. So I get 1 over R1 over R1 plus R2. And this is therefore 1 plus R2 over R1. So feedback gave me the more general result. Even if A is not infinite, I know AF is A over 1 plus beta A, and I get this more general expression when A is finite, which becomes this if A goes to infinity, and is exactly equal to this expression that we derived previously, assuming the op amp is ideal and without knowing anything about feedback, just using circuit theory. So this non-inverting op-amp amplifier is a really nice illustration of feedback. It's a great example of a feedback amplifier. Another exercise. Here's a feedback amplifier. And here we want to identify some quantities, like what is the input quantity, output quantity, the sense mechanism, the mix mechanism, where's the A block, where's the beta block, is the feedback negative. Okay, so this is an amplifier, and we see here that there is feedback. There is this element RF going from the output towards the input. So there is some feedback there. So I have an amplifier, but because this RF is feeding back the output towards the input, this is a feedback amplifier, and we want to analyze it using feedback theory. All right. Let's start with the first question. What is the input quantity? Well, because the input source is a current source, IS, the input quantity is a current. Well, that's kind of obvious. Output quantity, well, again, looking at the circuit, we're identifying V out here as the output quantity, so voltage. What is the sense mechanism at the output? All right, now the output quantity is a voltage, and the sense mechanism at the output would be the mechanism I use to measure the output voltage or to get to the output voltage. So how am I measuring the output voltage? V out is the voltage at this node, and it's to ground. So it's the voltage to ground. So this is ground here, and V out is this. So that's the output plus minus. So how am I sensing it? What's the sense mechanism? Actually, this wire and a wire here that we are not showing. So this is V out. And this is the sense mechanism. So as if I am taking this quantity and I want to measure it. It's a voltage. So I measure it in parallel using an imaginary voltmeter. So that's the sense mechanism. We call this shunt. And this quantity V out is being measured in the beta block. So the beta block is somewhere here to produce the feedback quantity that I will mix with IS. Mix in this case means subtract from IS. So how am I mixing? How am I subtracting the feedback quantity IF from the current IS? IF and IS are mixed here, and it's the KCL equation that will do the mixing. So the feedback current would be this current, IF. This will be the input current, the difference between them. And just KCL, by just connecting the wires to the same node, would make this current equal to IS minus IF. So that's the mixing. And also it is in parallel, so shunt. This type of amplifier, when the input is a current and the output is a voltage, is called a transresistance amplifier. Because it's controlling the output voltage from an input current. So transresistance. So this is the mechanism at the input. We are subtracting currents using the KCL equation. Now we want to identify the A block and the beta block. Let's start with the beta block actually. Beta is the block that produces the feedback quantity from the output. So it's the block that produces, in this case, IF from VO. And it's simply this. That's it. That's my beta. RF connected this way takes the output voltage here to produce the feedback current IF. So this feedback block can be a very simple, like a resistor to resistors. And we'll see many of those really simple feedback blocks. So that's it. That's the beta block. Where's the A block? For the A block, pretty much everything else would be the A block. So all of this would be A. So that's A and that's beta. And you see here, we're sensing the output, taking it to the beta block, producing the feedback quantity. There's no sigma circle again here. The sigma circle is hidden inside this node. The node implements the subtraction. So that's my feedback system. The last question is the feedback negative? How do I show that the feedback is negative? I need to show that A and beta have the same sign. So I need to show that the product A times beta is positive. So either A and beta are both positive or A and beta are negative. I don't need to calculate A and beta. The question is just to show that the feedback is negative. So I just need to know the sign of A and beta. So we can follow the flow of the quantities. So this is the input current here. It flows in the MOSFET like this. This is signal ground when you're talking about signals, to produce a Vx, a voltage Vx. So Vx between this node and the input quantity, I have a plus sign. So this is plus, right? Because this current continues like this, flows in RD1 and produces Vx. So Vx is RD1 times this current. And therefore there's no inversion between the current and Vx. There's no minus sign. And then this Vx is the voltage at the gate of M2. And VO is the voltage at the drain. But we know that when we go from gate to drain of a MOSFET, and we're considering voltages, there is a minus sign. There is a negative gain. So here VO, I will have a minus sign. So from gate to drain, there is an inversion. From gate to input current, there's no inversion. Overall, I can say that A is negative. I don't need again to calculate it, just know that it's negative. All right, so for the feedback to be negative now, I need to show that beta is also negative. Beta is the feedback quantity IF divided by V out, divided by the output. And if you look at the circuit, V out is plus minus like this, and V out produces a current like this in RF, but IF is in the opposite direction. So again, beta is negative because IF is flowing like this, and V out is plus minus like this. And I have a resistor here, just a resistor inside the beta block. So beta is negative, A is negative, and therefore the feedback is positive. Feedback is negative. So here's the circuit again with the results. The A block is the purple block, the beta block is the gray block, and A is V out over IN, beta is IF over V out, and both are negative. Their product is positive, and therefore the feedback overall is negative. Here's another example where I have an amplifier, looks like a differential amplifier here, with the input being here at Vs and the output being here at I out. This is just a block. We don't need to worry what's inside it, just like a load where the current I out is flowing. So again, we'd like to identify the input quantity, the output quantity, and the sense mechanism at the output and the mix mechanism at the input. All right, so the input quantity is Vs, and therefore it's voltage. The output quantity is I out, and therefore it's current. All right, so this is a transconductance amplifier because the input is a voltage and the output is a current. What is the sense mechanism at the output? The sense mechanism at the output, let's look at the output current. I out is flowing in this laser device and then in RM. This is a MOSFET, and therefore there's no current flowing here. So I out continues and flows in RM. And this is how I am kind of measuring I out. It's a series sense mechanism. I measure the current by adding a virtual ammeter in series with it. So there's like a virtual ammeter here in RM that's sensing I out. And what does it produce? It should produce a feedback quantity here, which is a voltage, Vf. And it does, because when the I out current flows in RM, I get a Vf, I get a voltage here, which is I out times RM. So RM is implementing the beta block. And so again, it's a very simple beta block, just something like this. RM, the output quantity comes, this is I out, the output quantity, and the feedback signal Vf would be simply I out times RM. Actually, this gives us the value of beta without much effort. Beta is RM in this case. So this is the sense mechanism at the output. The mix mechanism at the input, in this case, is interesting. I want to subtract VF from VS. So how do I do that? I'm using the differential pair M3 and M4 to amplify the difference between VS and VF. We know that the differential amplifier amplifies the difference between the two inputs. So I'm taking advantage of this fact to apply the feedback quantity at this input and the source at this input. M3 and M4 in this type of circuit and this differential amplifier would amplify VS minus VF. Because the differential amplifier amplifies VS minus VF, I just got the difference between the two. So the mix mechanism at the input is series, but using a differential amplifier. So the beta block, we already identified it. This is the beta block, it's RM. And everything else is pretty much A. And we can show that A is positive and beta is positive. We already have the value for beta. And A times beta is therefore positive and the feedback is negative.